Meet Zeno of Elea, born around 490 BC in a Greek colony in southern Italy. Zeno built a set of paradoxes, a series of arguments meant to make motion itself look impossible. The most famous of them is called the dichotomy paradox of motion, or more simply, the halfway paradox. It begins with a simple act, trying to cross a distance. Imagine you want to walk across the room to a wall just over there. Simple enough. But Zeno asks you to slow down and watch what crossing actually takes. Before you can reach the wall, you first have to cross half the distance. Then, from there, you have to cross half of what's left. And then half of that, and half of that, and half of that again. No matter how close you get, there's always another halfway point still ahead of you. Always one more step to take, which means to reach the wall, you'd have to complete an infinite number of steps. And how could anyone ever finish an infinite number of steps? So Zeno's conclusion is unsettling. You never arrive. Motion itself is impossible. But of course, you do cross the room. You do it all the time. So where's the trick? For 2,000 years, mathematics gave one answer. Yes, there are infinitely many steps, but they get smaller and smaller and smaller, and infinitely many shrinking pieces can still add up to a finite whole. Half the distance plus a quarter plus an eighth plus a 16th keep going forever. Eventually, it settles on exactly one. One room, crossed. So the paradox dissolves. You arrive because that infinite sum converges to a single finite distance. It's a beautiful answer, and it held for 2,000 years. But it quietly smuggles in one assumption that you can keep having forever, and that is the assumption we're about to break. So let's go back to that gap, the sliver of distance still left between you and the wall. Zeno says, cut it in half, then half again, forever. But can you actually keep having forever? If this were true, you would have to cross infinite steps in a finite amount of time. Yet you do reach the wall. Zoom in, past the width of an atom, past the particles inside it. Keep going smaller and smaller until you reach a scale so tiny it has its own name, the Planck length, about 100 billion times smaller than a single proton. And here, as far as we can tell, something strange happens. There may simply be no halfway left, no smaller gap to cut. You don't cross the room because infinity politely adds up. You cross it because the infinity was never there. The infinity is an illusion created by applying infinite mathematics to a finite universe. Since we know motion is possible, and we know we can cross the room, there has to be a better way to explain Zeno's paradox, a simpler way, one that does not require infinite convergence, hand-waving, or pretending the runner needs a philosophy degree before touching the wall. Instead of cutting the distance in half forever, let's do something easier. Let's count it. My elementary school teacher taught me the best way to get from point A to point B was to take the bus. RTD, rate times time, equals distance. But here, we are going to use it in the simplest possible way. Let R be one Planck length, the smallest meaningful unit of distance we can talk about. Let D be the full distance to the wall. And let T be the number of steps. At T equals 0, you have moved nowhere. At T equals 1, you have moved 1 Planck length. At T equals 2, 2 Planck lengths. At T equals 3, 3 Planck lengths. And so on. Not halfway again, not an infinite staircase shrinking into the wall. Instead of an infinite series of halfway steps, we now have countable motion, one smallest step after another. If the wall is 1 meter away, then the number of Planck length steps is about 6.19 times 10 to the 34th power. That number is almost impossible to imagine, but it has one very important property. It is finite. Zeno's paradox needs the distance to be infinitely divisible. But if the distance can be treated as a sum of smallest units, the infinite staircase disappears. And more importantly, We now have a function that can describe your position at any given t. Your position is simply distance traveled equals rate multiplied by time. The room is not crossed by completing infinity. It is crossed by exhausting a finite count. Now there is one important thing to call out. In this model, t is not ordinary clock time. Not yet. T is the step count. It is the moment number, the measurement index. The observer only updates the position when there is a new smallest change to observe. So at t equals 0, nothing has moved. At t equals 1, one smallest distance has been crossed. At t equals 2, two smallest distances. Each tick of t is not just time passing. It is the observer saying, measure again. And here is where it gets interesting. Just as there is a smallest meaningful distance we can talk about, the Planck length, there is also a smallest meaningful interval of time we can talk about, Planck time. The time it takes light to travel one Planck length. So now the equation becomes more than a counting trick. One Planck length per one Planck time, one smallest distance, one smallest tick, one discrete update of the universe. And if you divide Planck length by Planck time, you get the speed of light, the universal speed limit. So the same idea that breaks Zeno's infinite staircase also reveals something deeper. Motion is not an infinite blur. It can be described as a finite count of smallest distances across smallest moments. And the fastest anything can update through that count is c. So Zeno was pointing at something real. He was right that if you could keep dividing space forever, motion would become impossible. But the hidden assumption in his argument was that space can be divided forever. Once you accept that there is a smallest possible distance, the Planck length, and a smallest possible moment, Planck time, the infinite staircase disappears. There is no endless series of halfway points. There is only a very large but finite number of smallest steps. And because those steps are smallest and indivisible, your position at any moment is no longer a point on a smooth line. It becomes a count, a number. Motion is no longer something you approach through infinite convergence. It is something you enumerate, one smallest step after another, across one smallest moment after another. And when you divide the smallest distance by the smallest time, you don't get an arbitrary speed. You get c, the speed of light, the fastest rate at which the universe can update from one innumerable state to the next. Zeno thought he had proven motion impossible. What he actually revealed is that the universe has a grain. And because it has a grain, motion isn't an infinite blur. It's countable. It's exactly that it can be counted which makes motion possible.